Hello everyone and welcome to my lecture on resonance part 10. Here again we are going to discuss how resonance governs the mode of reaction, taking acid derivatives as example. Now what are acid derivatives? They are compounds derived from carboxylic acids. Some examples are acid chloride, ester, acid anhydride, amide, etc. Now, why are they called acid derivatives? Do they satisfy the definition of acid derivatives? Yes. Acid chloride, ester, amide, acid anhydride can be derived from carboxylic acid and therefore they are called derivatives of carboxylic acid. Just like acid chloride can be obtained from carboxylic acid by treatment with thionyl chloride, oxalyl chloride, phosgene, phosphorus pentachloride. Esters can be derived from carboxylic acid by treatment with alcohol, alkyl halide, etc. Amides can be obtained from carboxylic acid by treatment with ammonia. And acid anhydride can be obtained from carboxylic acid by treatment with phosphorus pentoxide. Coming to the reactivity of the acid derivatives. Are all the acid derivatives equally reactive? The answer is no. Different derivatives have different reactivity. Why? To understand this, we need to understand some basic concepts, so let's look at the molecule. Acid derivatives can be represented by the general structure RCOY, where Y is equal to Cl, or in the case of acid chloride it is a Cl, in the ester it is OR dash, anhydride OCOR, and amide Y is equal to NH2. Now if you look into the structure, the carbonyl group here, focus on the carbonyl group here. This CO double bond is made up of two atoms which are having different electronegativity. Oxygen is more electronegative than that of carbon. And since oxygen is more electronegative than that of carbon, it pulls the pi electron more towards the oxygen. And hence the oxygen, the electron density around the oxygen atom is more than that of carbon. And this makes oxygen to gather a partial negative charge and carbon gathers a partial positive charge. Now these type of acid derivatives can undergo nucleophilic substitution reaction, where the attacking group is a nucleophile. Nucleophiles are electron-rich compound, and so obviously it will attack the carbon which is positively charged. So the more positive the carbon is, the better is the reaction. So therefore, in nucleophilic substitution reaction, the more positive the carbonyl carbon, faster is the attack by nucleophile. And this is called electronic factor. The next factor that operates here is the steric factor. To understand this, we need to look into the mechanism of the reaction. This is the mechanism of nucleophilic substitution reaction on acid derivatives. These type of reactions are usually catalyzed by acids. The first step is the addition of acid. Acid generates H plus ion The H plus ion first goes and attack the oxygen atom of the acid derivative, because there is an availability of the lone pair electron on the oxygen atom. So when the proton goes and attacks the oxygen atom, the oxygen becomes positively charged. Oxygen being more electronegative than that of carbon, and on top of that it is having a positive charge, so it pulls the pi electron more and more towards itself, making the carbonyl carbon more positive. And therefore we can say that the electrophilicity of the carbonyl carbon increases by the addition of acid, and therefore this reaction is called an acid catalyzed reaction. Now, as the electrophilicity of the carbonyl carbon increases by the addition of the acid, the nucleophile can readily attack the carbonyl carbon, leading to the formation of an intermediate, which further leads to the product. Now here, as we go through the reaction, as the reaction goes forward, the starting material, as the starting material goes to the intermediate and then to the product, there is a structural change. The starting material, which is trigonal and has a bond angle of 120 degrees, when it goes to the intermediate, the structure is tetrahedral. The bond angle is 109 degree 28 minutes. And when it goes to the product, again the structure is trigonal and the bond angle is 120 degree. So we can see that as we are going from the starting material to the intermediate, the bond angle is decreasing, and therefore if there are large groups around the central carbon atom, there will be a lot of steric crowding among the groups in the intermediate state, and this will slow down the reaction. Therefore, smaller the groups around the central carbon, lesser is the steric crowding at the intermediate state, and faster will be the reaction. We will discuss more about the reactivity of the acid derivatives in the next lecture. In the next lecture, we will see that why the reactivity of acid chloride is more than that of other derivatives. In summary, the reactivity of acid chloride is dependent on two factors, one electronic and the other steric. That's all for today's lecture. If you liked my video, please subscribe, share, like and comment. Thank you and bye-bye.